Have you ever wondered how we can protect the incredibly delicate information in quantum computers from all the noise around them? It is like trying to keep a whisper clear in a roaring crowd. Logical qubits are encoded using physical ones by pooling together multiple noisy physical qubits to form a single, more robust, and error-resistant quantum unit. This clever strategy effectively shields the valuable quantum information from environmental disturbances. The fundamental reason we need this encoding is the extreme fragility of individual physical qubits. These tiny quantum systems are highly susceptible to noise, such as temperature fluctuations, electromagnetic interference, and even stray cosmic rays, which can cause them to lose their quantum state, a process known as decoherence. Unlike classical bits, which can be easily duplicated for redundancy, quantum information cannot be perfectly cloned due to the no-cloning theorem. This means we cannot simply make backup copies of our qubits. Therefore, to perform meaningful quantum computations, we must find a way to protect this unique quantum information without directly observing or copying it, which would destroy its quantum properties. The encoding process typically involves distributing the quantum information of one logical qubit across several physical qubits. Instead of storing a 0 or a 1 in a single physical qubit, that quantum state is entangled across a small ensemble of them. When errors inevitably occur on some of these physical qubits, we perform a process called syndrome measurement. This involves carefully measuring certain properties of the ensemble without directly measuring the actual logical state itself. These measurements reveal information about the type and location of the error, allowing us to deduce what went wrong. Based on the detected error syndrome, a corrective operation can then be applied to the affected physical qubits. This repair mechanism helps restore the overall logical state, ensuring it remains intact and accurate. A well-known example of this approach is the surface code, which arranges physical qubits in a two-dimensional grid, using local measurements to detect and correct errors in a highly efficient manner. This constant cycle of encoding, syndrome measurement, and correction allows us to maintain the integrity of our quantum information. This intricate dance of encoding and error correction is absolutely vital for overcoming the inherent instability of physical qubits. By distributing quantum information and intelligently detecting errors through syndrome measurement, we push towards a critical milestone known as the fault-tolerance threshold. Crossing this threshold means that the rate at which we can correct errors outpaces the rate at which new errors occur, making complex quantum algorithms finally achievable. Ultimately, the ability to encode logical qubits from physical ones is not just a technical detail. It is the cornerstone for building practical, large-scale quantum computers that can unlock truly transformative applications.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.